AP Calculus Notes Section 1.2, Understanding the Limit, an algebraic approach. So just a reminder, review, what is a limit? Well, it's the y value the graph gets closer to as x approaches a number. Notice it doesn't say the y value the graph is. It's getting closer to. It's becoming closer and closer and closer. Technically, it never actually gets there. Methods for finding limits. Method 1, examine the graph. That's usually the easiest thing to do. 2, direct substitution. That's generally super easy as well, almost as easy as looking at a graph. If 1 isn't an option and 2 isn't an option, then option 3 perhaps, simplify and then try substitution. Simplifying usually means factoring and then canceling out common factors. When that happens, there is a hole. And that's why direct substitution wouldn't work, is because there was a hole in the graph and you substituting in, it just falls right through. Rationalize if you see square roots. That is cumbersome and only works well if the problem is well thought out in advance by the person making up the problem. This method here is awesome. Number 4, and that eliminates the need to ever have to factor or rationalize. That's L'Hopital's rule. It's French. L'Hopital, L'Hopital. Unfortunately, we can't learn this rule for a long, long time. We can't learn this rule for a long time because you have to know all the derivative rules for this to work. So we will come back to this at some point. We are going to be focusing on these 3. We're going to learn this later. And L'Hopital's rule only works for indeterminate forms. That's when you try to figure out what the limit is and you get 0 over 0, or infinity over infinity, or negative infinity over infinity. Once again, we'll learn that later. When a function is defined and continuous at a value x equals a, how can this limit be found analytically? Well, that's by option number 2, direct substitution. So the limit of f of x as x approaches a is simply f of a whenever the function is defined and continuous at this a value. You're hoping that happens every time because that's super, super easy. Let's check out an example. Write the equation of the piecewise defined function pictured. You will note there are 3 pieces. There's a linear piece, a quadratic piece, and another linear piece. Let's focus on the constraints first, like the different domains for this. So for example, we have this green graph, which we're going to write here and here. We have the purple portion, which we'll write here and here. And then we have the blue version, which we will write here and here. The order in which you write these really doesn't matter, but typically we write it in the order that the domain is from left to right. In that first green part, it is going from negative infinity to negative 3, or we could just simply say x is less than negative 3. The purple part is going to go from negative 3, doesn't include it, and then goes until it gets to 2, and it does include 2, so we're going to put an equal sign. And then the blue domain is going to go from 2 forever to the right, which I'm just going to write that with the x first because that's better for me. X is bigger than, but not equal to 2. Going back to this green curve, by the way, even if it's linear, we can refer to it as a curve, as I just did. Going to this green curve, it is definitely a line. And if we were just to count spaces and look at what the slope is, slope's negative 1. If I extend this, it's going to have a y-intercept of -5. There are more precise ways to figure that out if it doesn't line up well. So it's f of x equals -x minus 5. Should point out this f of x equals this, and it equals this, and it equals this. We don't have to write y equals because it's right there. Let's skip down to the blue one. We'll get to the parabola last. This blue one has a slope of -1/2. And it looks like if we continue the pattern up 1 to the left 2, it's going to have a y-intercept of -1. So those are pretty simple. Going to this purple one, what we would like to know is where's the vertex? Well, the vertex is clearly here at -1, -6. So in vertex form, which is going to look like this, the y-intercept is -6. We translated it down 6. And we went to the left 1. So that means we're subtracting a -1. Or you could just write as +1. So all goes back to our translation rules that we learned in pre-calculus. And then, is there any change to the scale? So let's see, starting at the vertex, if you go right 1 and square it, you get 1. If you go right 2 and square it, you get 4. There's no change in the scale, it's just like the parent. So this is our piecewise function. Number 2, use the equation that you wrote to find each limit. So don't look at the picture, just use the equation. So first of all, this says x is approaching 2 from the right. You got to ask yourself, which of these domains includes 2 from the right? This one includes 2, and this one also includes 2. When I say includes, I mean 2 is on the boundary or part of the interval. So which one do we choose, this one or this one? Well, which one of these has 2 from the right? That is the blue one. X is bigger than 2, it means we're using x values that are to the right of 2 on a number line. So the first thing we want to do is we want to rewrite this problem using the specific piece of the function that we're referring to, and that is -1/2 x minus 1. We can use substitution for this, because if we use substitution, it's going to be defined. -1/2 times 2 is -1. -1 minus 1 is -2. So that's easy. This next one, we're supposed to approach 2 from both sides, the left and right. We've already done it from the right up here. If you recall the limit existence theorem that we had yesterday, for a limit to exist, a two-sided limit, the left and right limits have to agree. Well, we've already found the right-sided limit here. So let's do some work down here. Well, let me write down what we're trying to accomplish. We want to know, does this equal the limit of f of x as x approaches 2 from the left? And does that equal the limit of f of x as x approaches 2 from the right? Are those three equal? Specifically, are these two equal, which then in turn is going to make this be the answer to this? So let's check this out. Let's look at the domain for this. We want to approach 2 from the left right now because we already approached it from the right. Approaching 2 from the left, that is numbers to the left of 2, but close to it. That's in this purple domain. So we are going to be finding the limit of f of x as x approaches 2 from the left, which means we're finding the limit as x approaches 2 from the left of the parabola x plus 1 squared minus 6. And once again, we can use substitution for this. Replace the x with a 2. Now you might be asking, how do I replace this x with the 2 from the right or the left? What's the difference? Well, when you put the 2 in, it doesn't make a difference. This left or right is determining which piece of the function you're going to use. once you have the piece of the function in, you're not concerned with the left or the right part, you're just putting the 2 in. 2 plus 1 is 3. 3 squared is 9. 9 minus 6 is 3. So we ask ourselves the question again, is the limit of f of x as x approaches 2 from the left equal to the limit of f of x as x approaches 2 from the right? And the answer is no. It is no, because we found up here that if you approach from the right, you get -2, and then down here, if you approach from the left, we get +3. Those are clearly different numbers. Our conclusion from this, because you might have lost track of what the question was. The question was, what is this limit here, the two-sided limit? Therefore, the limit of f of x as x approaches 2 does not exist. The limit existence theorem says for it to exist, the left and rights have to agree. Direct substitution. This is just telling us, hey, use direct substitution. So that must mean, according to this right here, that this function is defined at the x value we're going to be given, and it's also continuous at that x value. So this is super easy. This really probably should be in parentheses. Direct substitution, we're going to have 2 times pi over 2, which is pi. So if you were to graph this, as x approaches pi over 2, the limit, that is 2 times theta, is going to approach pi. As the x value approaches pi over 2, the y value approaches pi. Number 4, using direct substitution, we're going to have cosine 2 pi over 3 over 2 pi over 3. Now, hopefully you're thinking, oh, unit circle, this is exciting. Sure, it's exciting. 2/3 pi is going to fall in quadrant 2. And what we really would like to know is, what's the reference angle? Well, that reference angle is going to be pi over 3, which is equivalent to 60 degrees. Now you can do this 30, 60, 90 in lots of ways. The way I prefer to do it, and will likely always do it in calculus, is I will choose the smallest side of a 30, 60, 90 to be 1. We will not use degrees in calculus, ever. So right now you would set your calculus to radians, you would leave it in radians, except for when you go to physics class, and you would change it back to degrees. So this up here, pi over 6 is 30. Opposite that, I'm going to call 1. And then opposite the pi over 3, which is going to be the long leg, is going to be 1 times the square root of 3. And the hypotenuse is twice the size of the short leg. Now, before I move away from this, I have to keep in mind which quadrant I'm in. I went left, so that means the x value is -1. I went up, the y is positive square root of 3, and r is always positive. Cosine is x over r, so that's -1/2. In calculus, here is a beautiful thing about this class. When you take the end of course test for this, the AP Calculus exam, if it's a free response question in which you can put down your own answer, you don't have to simplify anything, which means you can leave this horrifying mess as an answer. To the contrary, if you're doing a multiple choice question, you have to simplify it in whatever way they have simplified it. They are not going to simplify it by just leaving it like this. So let's get some practice here. For if it's multiple choice, you got to get your answer in their form. If it's free response, whenever you get your numbers in, you can just stop. So I'm going to multiply this by 1 in the form of 6 over 6. What was that do for me? Well, 2 goes into 6 3 times. 3 goes into 6 2 times. Going to be left with -3 over 4 pi. If this was multiple choice, that would likely be how the answer was written. Number 5, logarithms. Yummy. The directions say use direct substitution. So this is going to be log base 8 of 11 minus 9. 11 minus 9 is 2. This is asking the question. 8 to what exponent is 2? Should be a game show. Now you can continue with this in lots of ways. One way is to get the base of the logarithm 8 and the base of 2 to have the same base. Is there a way to write 8 that has a is there a way to write 2 that has a base of 8? And the answer is yes, because the cubed root of 8 is 2. One of the properties that we had for logarithms, if you have log with a base and your argument is the same base, this whole thing just becomes the exponent. And there are lots of reasons why that is true. And if you would like to know any of such reasons, drop me an email, send me a message on Remind on Google Classroom, and I will make an explanation for that. This time we're supposed to simplify and substitute. So this graph is here for reference only, just to try to make sense of what's going on when we get these strange answers. So we'll come back to this graph here in a moment. Please note, so don't write this down, but work with me here. If I were to plug a negative 3 into the denominator, negative 3 squared is 9, and then a negative 3 times 2 would be subtract 6, and then we also subtract a 3, this denominator would be 0. Dividing by 0 is undefined. That is why direct substitution will not work for this. If you put negative 3 into the top, you would also get 0. When that happens, 0 over 0, we could use L'Hopital's rule, but as I mentioned earlier, we have not learned that yet, and we'll not learn that until the very end of the school year, unfortunately. So we're going to have to figure out what's going on and what's likely happening since we got 0 on the top and the bottom. There's a hole in this graph. How do we find holes? Well, we factor. Please note, until you evaluate the limit, you have to keep using limit notation, the limit as x approaches negative 3. The numerator factors into an x plus 1 and an x plus 3. The denominator factors into an x minus 1 and an x plus 3. We can cancel an x plus 3 from the top and the bottom. And what do we know is happening with our graph? We know that means there's a hole there. So if you look back here to this graph, we just tried to use direct substitution and put an x value in of negative 3 to figure out what the y value is. And we came up short because if you try to do that, it just slips right through. This does not tell you what the y value is unless you're staring at the graph. Even at us staring at the graph, we know the y value is between 0 and 1. Maybe it's a half. We'd be estimating if that's what we thought. So going back to the algebra, we now have the limit as x approaches negative 3 of x plus 1 over x minus 1. Now if we use substitution, it's no big deal because we're going to have 3 plus 1 over negative 3 minus 1. It's going to be 4 over negative 4. That's, hold on a second. Oh, I'm sorry, this is a negative 3. That would make this negative 2 over a negative 4, and that's going to be a 1/2. So what's the limit? As x approaches negative 3, it's 1/2. And our graph verifies that. If we approach negative 3 from the left or the right, it's approaching the same number. It appeared to be 1/2. Algebraically, we just showed, boom, it is 1/2. Number 7, as x approaches negative 1. Now, this is the same function that we had above, so I might as well use the simplified version of this. I'm sorry, it's x is approaching positive 1. from the left. Now the problem here is if we try to use substitution into this, this is going to be 0 still. So what do we do? Now if you look at the graph, we know what's happening. There's a vertical asymptote. But without the graph, would we know if we're approaching from the left, is it going to be going down or is it going to be going up? And here is a cheating way to do that, using the word cheat very loosely. I'm going to make a table, try to explain what I'm doing. In this table, we're going to choose a value of x left of 1, something close, like maybe a 0.9. Depending on your perspective, 0.9 is close to 1 from the left. And then we're going to use the simplified fraction, which is y equals x plus 1 over x minus 1. And what we're concerned with here is we put a 0.9 in on the top and bottom. Is our answer going to be positive or negative? You put on the top, you're going to get 0.1. On the bottom, you're going to get negative 0.1. Top, you're not going to get that. You're going to get 1.9 on the top. If you divide those, what's your answer going to be? It's going to be positive or negative. Well, we were really close to 1, I mean relatively, and this ends up being a negative answer. We end up with a positive over negative, which then what that means is we're assuming that this is going to be approaching negative infinity. If you look at your graph, we can see that that's what's happening. As we approach, this is 1 from the left, the graph is going down, down, down to Chinatown. So we would say the answer to this is negative infinity. Does the limit exist? No, it's not a number. Same question, but from the right. So let me copy some of this down here. Make changes as I need to. Here we're approaching from the right. And we want to choose a number from the right of 1. Such as 1.1. So we got 1.1 plus 1 over 1.1 minus 1. That's going to be 2.1 over 0.1. That's a positive over a positive. If you divide two positives, you're going to get a positive. So what I'm suggesting here is this is leading us to believe that it's going to positive infinity. Now, before I get away from this, let me re-examine this, and I want to make sure we're coming to the right conclusions. Are we saying that every time we evaluate a limit, and when you can't use direct substitution, that you see if it's positive or negative? If it's positive or negative, then it's going to infinity or negative infinity. We are not saying that. We are saying that if we know the graph has a vertical asymptote, which this clearly has one, and it's the same function. There's a vertical asymptote at x equals 1. We know that because a non-canceling factor in the denominator is here, this x minus 1. What we don't know is if we approach from the left, is it going up or down? As you approach from the right, is it going up or down? This is telling us, as you approach 1 from the left, the graph's going down. As you approach 1 from the right, the graph is going up. This is telling us asymptote behavior using these limits. I would say that would be a good place to stop for day 1 of these notes. So stop this now, do as much of the homework as you can, and I will continue with these notes. You can pick up right where you left off tomorrow. Well, welcome back, it's tomorrow. Simplify and substitute, rationalize and cancel. Last time we simplified and substituted, we factored and canceled. So the graph of the function g of x, which is this hot mess, is pictured. Often, not always, rationalization can be used to evaluate the limit analytically. So find the following limit. And we're going to find this algebraically, and then we're going to use the graph to confirm what is happening. So clearly, so here's the part that is perhaps vexing for us. Clearly, this graph has a hole at x equals 3. You can see it. In order for that to happen, we would have to have canceled a factor of x minus 3 from the top and the bottom. But if you look, there is no factor of x minus 3 on the top, or at least it doesn't appear to be. So this is a little misleading in its current form. We need to fix it so that we can clearly see that we're canceling an x minus 3 from the top and the bottom. So to do that, we are going to multiply this fraction by 1, as we often do. And 1 is going to take the form of the conjugate of this fella in the numerator. So that's going to be the square root of the sum of x and 1 plus 2 over the square root of the sum of x and 1 plus 2. Emphasis on the plus. Most common mistake students make is they put the same sign that was in the original problem. The conjugate is the opposite sign. When you are doing this, when you're multiplying the conjugates, multiply those together, whether it's in the numerator or denominator. When you're multiplying non-conjugates, like you are in the denominator, do not multiply it out. Just write that you're supposed to be multiplying it. It is of no value to multiply it out. When you multiply two conjugates, you're going to get the first term squared minus the last term squared. There's also two middle terms. One's positive and one's negative, and they have the same value, and they always cancel out. So this is going to be the limit as x approaches 3. This denominator is not changing because we are not multiplying out things that are not conjugates. In the numerator, the square root of the sum of x and 1 squared is x plus 1. In the numerator, we are subtracting from that 2 squared. 2 squared is 4. Simplifying a bit more, we're going to have the limit as x approaches 3. In the numerator, we get x minus 3. Now that shouldn't surprise us, that the top became an x minus 3. The reason that should not surprise us is because we were trying to get a factor of x minus 3 in the top and the bottom so that they would cancel. Because when they cancel, we end up with a hole in the graph. Be careful. When these cancel, you're left with nothing on the top of a fraction. It means you're left with a 1. So now we have the limit as x approaches 3 of 1 over the square root of the sum of x and 1 plus 2. Can we use substitution for this one? We sure can, because once you substitute, you can stop writing limit notation. So we're going to have 1 over the square root of 3 plus 1 plus 2. Let's get my calculator out real quick. 3 plus 1. Oh, it's 4. Interesting. I did not see that coming. And then the square root of 4. Oh, it's 2. Very nice. This ends up being a 4th. If you haven't noticed, Notability has been driving me nuts lately. Once in a while, it will freeze that I can't choose these icons up here at the top. And the only way to get out of it is either close Notability entirely or to go back and then back again. So anyhow, here's what this is saying. The question was, what is the y value getting closer to on this graph as x gets closer to 3? What is the value of this hole, the y value? And we have just found definitively that the y value here is 1/4. Number 10, find each of the following limits analytically. Show your algebraic analysis. So we're going to try to use substitution, and if it works, great. If it doesn't, then we'll try something else. Well, it sure looks like substitution is going to work for this, because I'm not getting something that's undefined. What is natural log of e? Well, that is 1, of course. Let me remind you of why that's 1. Natural log of e is the same thing as saying log base e of e. Natural log means it has a base of e, which we don't typically write. So what's this saying? Let me color code this for your viewing pleasure. It's saying this red e is going to be raised to what exponent to equal this black e? This should be like a game show. Well, of course it's 1. E to the first is e to the first. That's why natural log of e is going to be 1. Number 11. Can we use direct substitution for this? Well, I don't see any reason why we couldn't. So we're going to have sine squared of pi plus 2 times cosine of pi. Please note, sine squared of pi, what this actually means is sine of pi, when you're finished, you're supposed to square it. This is a shorthand version of that. Well, what is sine of pi? Well, that's a 0, of course. 0 squared is 0. What is cosine of pi? It's -1, of course. 0 minus 2 is -2. Let me refresh your memory of how I know, and that you know, that sine and cosine of pi are what they are. Pi, in the coordinate plane, using radians, is the negative x-axis. In order to figure out what sine and cosine are, we have to know what x, y, and r are. Over here, let's say x is -1. You could choose any x value you want as long as it's negative. Y has to be 0. We didn't go up or down. R is the same value as x, but it has to always be positive. So sine, which is y over r, 0 over 1 is 0. Cosine of pi is x over r, that's -1 over 1. That's why that's -1. Number 12. Direct substitution works for this one as well. There's nothing bad's going to happen here. So we're going to have tangent of 5 pi over 3 over 5 pi over 3 squared. Remember, once you substitute this in for your variable, you do not write the limit notation anymore. Now, what is sine of 5 pi over 3? Well, first of all, which quadrant is that going to fall into? It's going to fall in quadrant 4, because that's going to make us just short of a complete revolution. How short does it make us? It makes us pi over 3 short. Which means this is a special right triangle. And I did not make that to a very good scale. Do I have to make it to scale? No. But you likely will appreciate if I do. That's better to scale. So the missing angle here is pi over 3, which is 60, which means this angle down here is pi over 6, which is 30. In calculus, I don't particularly use the unit circle per se. I always choose the smallest side of my special right triangle. This is a special right triangle to be 1. Opposite 30 is the smallest side. That's 1. That's an x value. That's the short leg. The long leg is that times the square root of 3. So y is square root of 3, kind of. I'll get to that in a second. And whatever's opposite 30, the short leg, the hypotenuse is double that. So we're saying r is 2. What about our signs, our positives and negatives? S, I, G, N. In quadrant 4, x is positive. In quadrant 4, y is negative. And r is always positive. Continuing with this bit of a mess, Tangent of 5 pi over 3, tangent, as we know, is y over x. So that's negative square root of 3 over 1, which is just negative square root of 3. Our denominator, how do you square a fraction? Well, you square the top and you square the bottom. So 5 pi squared is going to be 25 times pi squared, and a 3 squared is 9. If this was a free response question on the AP test, you would stop. Leave it a mess. They actually advise you not to simplify it because you might make a mistake and they don't want you to lose points on it. If this was multiple choice, you would likely have to simplify this. I'm going to multiply this by 1 in the form of 9 over 9. Multiplying this 9 times the top and this 9 times this fraction on the bottom. Fraction on the bottom, the 9's cancel. On top, 9 times the square root of 3 is 9 square roots of 3. There's a negative sign out there. On the bottom, we get 25 pi squared. That's it. Problem's finished. Number 13. Interesting. Direct substitution will not work for this. Because if we were to put 3 over 2 in for this, the 2's cancel. We'd have 3 minus 3 is 0. So it's NGH. It's not going to happen. So maybe we can factor this. So we have the limit. Remember, until you evaluate the limit, you have to continue to write limit notation. The bottom is already prime. It's factored. The top, this is the difference of two cubes. This is a cube whose cubed root is 2x. This is a cube whose cubed root is 3. So this is a 2x cubed minus a 3 cubed, difference of two cubes. Well, how does that factor? We take the cubed root of the first term, 2x, and then you use the same sign, which is subtract, the cubed root of the second term, which we're saying is 3, and that becomes a binomial for our answer. We're going to multiply that by a trinomial. What goes in the trinomial, we take this first term in our binomial and we square it. That is 4x squared. The last term of our trinomial is this last term in our binomial squared. 9 squared, or if you want to think of it as subtract 9 squared, either way. I'm sorry. A 3, not 9, squared is 9. And then this middle term, we're going to take the 2x times the 3 and get 6x. And then we're supposed to, I'll get to this, what we're supposed to do here in a second. So let me go over the signs here. There's an acronym that Mr. Paul taught you and Mrs. Allensworth taught you, which is SOAP. S stands for same. This first sign, the only sign in the original difference of two cubes, is going to be the same as the first sign here. So same. Second sign is opposite. Same, opposite, because plus is opposite of minus. And the last one is always positive. Same, opposite, always positive. Always positive, opposite, same. Anyhow, I'm sure you remember that from Algebra 2. We may have dabbled in pre-calc, but not much. We can cancel 2x minus 3 from the top and the bottom. What's that tell us? It tells us there is a hole. You know, once we get those holes, we got to plug those holes because otherwise people are going to die on the ship. So I have the limit as x approaches 3 over 2. It's no longer a fraction. Once you get rid of your fraction and you still are writing limit notation, if there's more than one term, you should put that, it's called the argument, you should put that argument in parentheses. Can we use direct substitution now? You betcha. So we're going to have 4 times 3 over 2 squared plus 6 times 3 over 2 plus 9. If this was on the AP test and it was a free response question, you would stop right here. If you're taking a test from me and it's a free response question, you can stop right here. If it's a multiple choice question, you need to continue. Let's assume it's multiple choice. We want to practice our algebra skills. By the way, 6 and 2, you can divide both those by 2. This is going to give us 3 times 3. Up front, 4 divided by 4, so we're going to have 9 plus 9 plus 9. That's 27. Backside, we got 4 more. If we try to find this limit directly, horrible, painstaking, awful things are going to happen because our denominator is going to be 0, which makes this undefined. So what do? We multiply this by 1 in the form of the conjugate of the binomial in the top, that radical. So we're going to multiply by 1 in the form of the square root of 2x plus 5 plus 1 and the square root of 2x plus 5 plus 1. If this was a plus, this would be a minus. It's the opposite. In an effort to emphasize my pluses, I made them so horrible that I couldn't tell what they were. So this is going to be the limit. By the way, write small. I got a lot of work for this. As x approaches -2. On the top, when you're multiplying 2 conjugates, you get the first term squared minus the last term squared. In the denominator, multiplying the 2 non-conjugates, just write them out that you're multiplying them beside each other, but don't actually go through the work and multiply it out. In the top, square root and squared are kind of like inverse operations. We pretend that they are. That's going to give us 2x plus 5. Then we subtract a 1 squared is 1. In our denominator, we're going to just leave that as it is. And then in our numerator, if we continue with this, we're going to end up with the limit as x approaches -2 of 2x plus 4. Oh no, this x plus 2 doesn't look like it's going to cancel. Well, that's a bummer. Now, could that happen where it doesn't actually cancel? Absolutely. But it's unlikely because people are specifically making up problems that they're going to cancel. So what happened? Did we make a mistake? No, there's a GCF here of 2. So we could rewrite this as 2 times the sum of x and 2. And then we could say, hey, you know what? I don't want to cheat like I just did. That's Bush League. If there was a league in which Bushes were there, what I just did would be in that league. So we're going to have 2 times the sum of x and 2 over the sum of x and 2, and then the square root of the sum of 2x and 5 plus 1. I left off my parenthesis up there as well. Now the x plus 2's cancel. So now we can substitute in for the x's, and the top is a 2. The bottom is going to be 2 times -2 plus 5, and then we add the 1 to it. Let's do a little bit of this in our head here. 2 times -2 is -4. -4 plus 5 is 1. Makes this the square root of 1. And then we're going to add a 1 to it, because that which was written here. This is going to be 2 over 2, which is going to give us 1. Wow, a lot of work. But it was worth it, wasn't it? Ooh, number 15. Wowzers. This is undefined in three locations. We put a 0 in on 2 locations. In for here and here, it's going to be undefined. So what can we do to fix this? Well, we can try to fix it by getting rid of our denominators. So to do that, I'm going to multiply every term by an x plus 2 and an x. It's the same as multiplying top and bottom by 1. And in the top, there's multiple terms, so you distribute. So this x plus 2 cancels, this x cancels, this x cancels. So what are we left with? we're left with the limit as x approaches 0. This first fraction is just going to be an x plus. The second fraction is going to be an x plus 2. Please note, this was a subtract sign. We have to put this in parentheses. It isn't, so we won't. And then down here, we have an x plus 2. Simplifying some more, we can combine like terms. We got the limit as x approaches 0. We got 2x plus 2 over x plus 2. Nothing seems to cancel. Oh, you know what? I made a mistake. I made a boo-boo. I said these x's cancel. They don't cancel. They're both on top of the bottom of this fraction. If I extend this line over, I'm saying I'm multiplying these three things together. Those don't cancel. My apologies. So it's going to be an x squared times the sum of x and 2. I'll leave it like that. If I factor a 2 out of the top, I'm trying to get things to cancel here. So I can substitute. And it doesn't. Nothing cancels. So that shouldn't make me uncomfortable, but it should make me wonder, did I make a mistake someplace? I didn't. I don't make mistakes. You've been with me long enough. If we put 0 in for this, it's going to be undefined. Nothing cancels. So this limit does not exist. Now, why would that happen? Well, let me tell you why it happens. It happens because this graph has vertical asymptotes at x equals 0 and -2. X squared is a non-canceling factor in the denominator, so it's going to be a vertical asymptote. X plus 2 is a non-canceling factor in the denominator, so -2 is going to be a vertical asymptote. So we can't evaluate the function as x approaches 0, because as x approaches 0, the graph either goes up or down forever, therefore the limit does not exist. All right, last two, 15, 16 and 17. These are the ones that are the least organic for me. Nothing simplifies here. We can't factor anything. Direct substitution will not work. So what's happening? We know there's a vertical asymptote at x equals 3. That's from pre-calc. X minus 3 is a non-canceling factor in the denominator, therefore x equals 3 is a vertical asymptote. So the question is, as this graph approaches the vertical asymptote, and I'm just going to draw a vertical asymptote like so. We got two choices. As x approaches 3 from the right, either the graph goes up like this, or it goes down like this. It's one of the two. We'd like to know which one it is. So to figure this out, we're going to make this table, and we're going to choose an x value that's to the right of 3, because this says from the right, such as 3.1. You want something close, like the number 4 is not close enough. It needs to be close. We're going to plug that into the 2x plus 5 over x minus 3. We don't need to know the numerical value. We just need to know, is it positive or negative? If you put 3.1 into the top, you got 2 times 3.1 plus 5. That's going to be positive for sure. If you put 3.1 into the bottom, 3.1 minus 3, that's also going to be positive. If you divide two positives, guess what you get? You get a positive. What's that tell us? That tells us that this is approaching infinity. We knew it was one or the other. Positive, so that means it's going up. Done. This one here, same thing, but we're approaching from the left. Let's make our table. Choose an x value to the left of 3, like a 2.9er. If you put 2.9 into the top, you're going to get 2 times 2.9 plus 5. I don't know what that number is, but I know it's positive. If I put 2.9 minus 3, I don't know what that number is either, dog, but I know it's going to be negative. You know what I'm saying? A positive divided by negative, negatory. That means this is going to negative infinity. Once again, we know it's going to positive or negative infinity because this has a vertical asymptote at x equals 3. All right, please finish the homework that you didn't finish from yesterday. And